momentum and impulse. So we have two carts with a spring between them. They are compressed, right? They are brought together, which is storing elastic potential energy, and then it is released, right? And that energy then converts into kinetic energy of both of the carts as they spring off of each other, right, and move outwards. Question A, the spring constant is 250 newtons per meter, right? In other words, every meter it is compressed, it will provide 250 newtons of resistive force. Calculate the total energy released from the spring. So as it's compressed, it is storing potential energy, and then when it is released, like let go, that energy is then converted, in this case, into kinetic energy. Now, looking at our data booklet, we know the equation for elastic potential energy, E subscript P, is equal to half times K times X squared, where K is the spring constant and X is the displacement of the spring, like how much you've compressed it relative to its equilibrium position, or how much you've pulled it back relative to that equilibrium. And in this case, X is 10 centimeters or 0.1 meters. So we have everything we need. And we're solving for energy. Right, so we can substitute in K, 250, X, 0.1, not forgetting to square it, right? That's a very common mistake. So what's that? 0.1 squared, that's a tenth squared, that's a hundredth. 250 divided by 100, 2.5, 2.5 times a half, 1.25 joules. Right, do check on our calculator though. So that's how much energy is stored in the spring and then hence released, assuming no energy losses. And that is an achieved question because we just substituted in some values and solved for a quantity. Alright, now we're told that the mass of the red car is 0.5 kgs and the mass of the blue car is 2 kgs, so a bit heavier. The final velocity of the blue car is 0.5 meters per second. I'll assume it's to the right. Calculate the final velocity of the red cart. Again, I'm going to assume they're bouncing off each other. So I'll just label that as VF for final velocity. So that's the setup. So we know some masses, so mass red, mass blue. We know the velocity, initial velocity of both of them would be 0. We know the final velocity of the blue cart, but we're looking for the final velocity of the red cart. So there's two main approaches here. You could take the conservation of momentum approach or of energy, right? Where energy would link to kinetic energy. So the total kinetic energy after they've separated must equal to how much energy was given by the spring. And the conservation of momentum idea is that the total momentum of the blue and the red cart should equal 0, right? Because the initial momentum is 0 when they're not moving. So I think I'll go with the momentum approach, but do try the energy approach as well for your study. So actually the first thing I'll do is write out the words conservation of momentum, PF, the final momentum, equals PI, the initial momentum. And what I mean by initial momentum is of the whole system. Not just of the red cart or the blue cart, but of both of them together. So Pi, the initial momentum, is the mass of the red car times its initial velocity, VIR. Added to that is the mass of the blue car times its initial velocity. And this one's super easy since they're starting at rest. Right, we are assuming that, but starting at rest, the initial momentum would be 0 kilogram meters per second. Alright, now the final momentum, mass of the red car times its final velocity plus mass of the blue car times the final velocity of the blue car. So that's 0.5 VF for the red car, that's actually what we're looking for, plus mass of the blue car, 2 kgs, times final speed of the blue car, which is 0.5. Alright, and we know that initial momentum must be equal to final momentum. So we can set this expression equal to 0. So 0 equals 0.5 VF plus 1, right? Because 2 times a half is 1. Now solving for VF, we will subtract 1 off of both sides, and we will divide both sides by 0.5 to get VF equals -2 meters per second. So what does the negative mean? Well, we assumed 0.5 was to the right, and that's positive. So we actually defined right as positive and left as negative. Which makes sense, right? The red car should go left. Okay, and actually just doing this calculation alone is only achieved, but with part 2 we can get merit, right? So let's just put a merit here because I know we're going to get it. What assumption, if any, good one, they're trying to trick you. Yeah, we make lots of assumptions in classical mechanics and physics. What assumption have we made? So it is an assumption that underpins conservation of momentum, or conservation of energy if you went that way. So we assumed a closed, or you could use the word an isolated system. And what that means is no external forces. In other words, there's no friction, right? Taking away energy or taking away momentum, it's entirely converted into the motion of each cart. Right? So this assumption goes hand in hand whenever you use conservation of momentum. And in fact, also with conservation of energy. Right? And together with that calculation, that is a merit. In a different experiment, the red and blue carts are set moving in opposite directions. Okay, as in one's going right, one's going left, where the blue cart is stopped by a solid board and the red cart is stopped by a padded wall. So let's go, red goes into padded wall, and blue goes into solid wall. And the key thing here is that they have equal momentum. right? It's not saying equal velocity, it's saying equal momentum. Alright, what's next? Use physics principles, okay, that makes sense, physics paper, to explain whether the blue cart or the red cart will suffer the most damage as they stop. Okay, so we know they're both going to stop as well. Okay, so what would the final momentum be? So for red, final momentum would be 0, right? Because it's come to a complete stop. In other words, its speed is 0, or velocity rather, and mass times velocity is momentum, which gives 0. For the red one, for the blue one, its final momentum is also 0. Again, it's come to a complete stop. So we could say that the change in momentum, delta P, is the same for both carts. Again, they start with the same momentum. They both end with a momentum of 0, final momentum. So the change in momentum is the same. They'll just be in opposite directions. So we could say that in opposite directions. Not necessary for this one though, because we're just worried about the magnitude. Okay, what else? You'll recall change in momentum is sometimes called impulse, right? It's the same quantity, and it's force acted on the object times the time of the collision. And to determine which will suffer more damage, we would be interested to know the force acting on the cart, right? If a massive force is acting on the cart, it will suffer greater damage than if it was a little force. And we've just said that delta P, change in momentum, is the same. What about the change in time? So padded wall will increase the time of the collision, right? It draws it out more. The cart will go with the wall will give way, it'll absorb more energy, so it'll increase the time of the collision. Resulting in less force and therefore less damage. Right? So the red car, since it's going into the padded wall, will have a longer collision time, and since change in momentum is the same, will experience less force and hence less damage. Right, and conversely, blue cart has shorter time, therefore more damage. Cool. All right. And that is a merit question. You'd get achieved if you only made one of those bullet points. So 1, 2, and like 3. And if you got all 3, that is a merit. Again, the key learnings from this question is you need to state what is the same, what is different, and how it influences the variable that you care about. So in this case, damage relating to force. Alright, and last question, D. We're given information about the blue cart and its collision time. State Newton's third law of forces in the context of the collision of the cart and the board. So Newton's third law, there is an equal and opposite reaction force. So that's Newton's third law in general. And what that means in this context, there is a force on the cart from the board, board. There is an equal and opposite force on the board from the cart. Right. So next time you accidentally walk into a pole, just keep in mind that even though the pole exerted, a pretty big force on you, you also exerted it back on the pole. So don't be too upset. And that's exactly what's happening here with the cart and the solid board. Okay, and if we got that, so far that's just an achieved. But together with part 2, that will give us excellence. So let's do that. Calculate the size and direction of the average force experienced by the board during the impact. Right, so it's the force that the board is experiencing, not the cart. But we know that they would be the same in magnitude and opposite in direction. So are we given the momentum of the cart? We are given the momentum beforehand, mass times velocity. Just writing the impulse equation before we get started though. We are looking for the force exerted. And to solve for that, we need the change in momentum and the change in time. Change in time is just the collision time, which we are given. So we need to calculate the change in momentum, where change in momentum is the final momentum minus the initial momentum. Okay. Now let's don't have a diagram or anything, so let's just draw one. So let's assume the blue cart is going right, 2 meters per second. So right is positive, and here is the board. So final momentum of the cart would be what? That's after the collision, and it came to a stop, so it would have a mass of 2 and a velocity of 0, right? Its final speed is 0, which gives us 0, and we take away the initial momentum, which is its mass, 2, times its initial velocity, which is 2 to the right, so it's positive 2, which gives us -4, resulting in a change in momentum of -4 kilogram meters per second. And the negative tells us that the change in momentum is to the left. Okay, now we can solve for force. Force equals change in momentum over time, -4 divided by 0.02, which gives us negative 4 divided by 0.02, negative 200 newtons. And what does that tell us? Is that the force that the wall experiences, or the board rather, or that the cart experiences? So this is the force that the cart experiences as a result of its change in momentum. So what is the force experienced by the board? So F board would be the opposite direction of that force, which is 200 newtons. And so that's 200 newtons to the right, because it's positive 200. So just to summarize, we would say that the board experiences 200 newtons of force to the right, as per my diagram. If you want to be a bit more general, you could say it experiences 200 newtons of force in the direction of the cart's initial velocity. Right? Notice how it's traveling to the right initially, and the force is positive to the right. So that would be a bit more general. But this is totally fine. Drawing your own diagram with your own coordinate system and being clearly communicating that. And that would be an excellence. High five. Alright, I'll see you next time.